Day 153. Last day of mechanical waves and sound. Tomorrow we're off to non-mechanical waves. That would be things like light, um, and so we're going to look at electromagnetic waves or E&M waves. Okay, 3 goals for today. You should be able to draw some wave patterns for objects moving at a variety of speeds and explain the cause of a sonic boom and explore some non-mechanical waves. So if you've already done the warm-up, fantastic. If not, go ahead and pause the video now. We've got a word bank for question number 1. So pause the video now and do it. Okay, so Jackson's going to show you some different planes in a bit because that has something to do with what we see today. Before we get to that, though, the warm-up. So the pitch of a sound depends on the frequency of the sound waves that reach the what? The observer or the sound generator? The observer. Oh, want to say hi?
Hi.
Where are you? There you are. Zoom. Oh.
Hi.
Where is she? Taking herself for a walk in a stroller. Woo. Okay. Number 2. In each case, tell whether the pitch rises. Rises or drops. So here we go. The source of the sound moves away from the observer. All right. So here's the observer. Okay. All right. And here's the sound. It's going to move away. So this means that the waves are going to be more spaced out than they normally would be because the sound generator is moving away. So if it makes a sound every put, 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 all right, they're going to have big spaces versus the source stays still and the observer moves towards the source. Okay, here's my observer. She's coming towards it. She's going to be closing the gap between each little sound wave faster. So then the pitch would rise for that one. The source and the observer move towards each other. So if this is making sound and the waves are coming out, wave, 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 if they're moving forwards, then the space between the waves actually decreases. And if this person is also moving forwards, then they're getting to each wave faster. Okay, this is like if you were running past a fence and it had fence posts, you would get to each post faster if you're running than if you were, say, crawling. Right? It would slowly get to each post. But if you're running, you run past each one really quickly. Okay, next. Last one, D. The source stays still and the observer moves away. So here's our source. Here's our observer. And the observer moves away. This is going to make it take more time for each wave to get from the source to the observer. And so the pitch is going to drop or decrease, drop. Okay. For classwork, we're going to do a little bit more Doppler effect. We're going to look at some examples and some uses of this because it actually gets used quite a bit. And then we'll talk about sonic booms. And then that's it for sound. Okay, so take a few minutes right now to take your best shot at answering these 3 sets of questions. And then come on back. Okay, so all the cases above, examples of, surprise, Doppler effect. And there's actually uses for this. Right? It's not just a cool thing. It has real world uses. You probably don't use it every day, although you might be able to use it to see if something was coming towards you or moving away. It's not that important most of the time, though. But things that affect you use it, like weather prediction. So weather radar uses this. And radar is something that sends. I'll show you. This is one of the links I've put down here at the bottom. Weather radar. And so here's an example of that. Here's the radar. It's a dish. It sends out a giant pulse of energy. And if that hits something like a drop of water, the energy bounces off and it comes back. And if this drop is, remember we were moving our little thing, if this is moving and the wave hits it, it's going to send the wave back with a tighter waveform, so more greater frequency, shorter wavelength. And so the dish will pick that up and go, aha, it's moving towards us. If it comes back with a longer wavelength, that means it was moving away. All right. So you can see not only where things are, and you can figure out where they are, by the way, by looking at how long it takes for the echo to come back. Or we've solved some echo problems, and this is where those echo problems get used in the real world. But also the frequency of the wave that comes back. That tells you how fast the object's moving and which direction. Pretty cool thing. Other uses, radar. Police officers use radar to see if someone's speeding. So same idea there. And a little link about that. Oops, it's not in here. JK. Here. And then also you can look at light and how... so you may know that different wavelengths of light make different colors. And if you're looking at a star and it changes color over time, like over many years, that means that it's changing direction. Same with a planet reflecting a star's light. You can see if it changes color, that it may be moving in a different direction. And that change in color is from either moving towards or away from the observer, and the waves, again, either getting shorter or longer. There's a comet, Halley's Comet, that came past the Earth in 1986. Wow, 7. And it's not going to be back until 2061. So right now, it's actually changing direction. It's on its way back towards the sun. It's way out in space, way out of the solar system, and in about 40 years, it's going to come back. And so it's changing color right now to observers. And one of the ways that they could figure out what it's going to do is by watching that color change over time. And by over time, I mean like over a period of a few months or maybe even a few years. Okay, so you all know for number 3, if you dropped a rock or a ball into a lake, it would make ripples. And those ripples would spread out how? Evenly or not evenly? Evenly. You get something like this. Right? Even ripples. What if, though, you were to drag something like a little boat or a stick through that water? Well, what would you get there? I'm asking you to draw 4 circles representing wave fronts. Okay, so here's some circles, 3. But showing what it would look like if the boat was moving. So I'm going to do that now. And there you go. And one thing you may notice is that they're kind of bunched up in the front because the boat is chasing the waves in the front, and they're spread out in the back because the boat is racing away from the ones in the back. All right, they're moving opposite directions. So think about that. That's for a boat that's going slower than the waves move. Think about what it would look like if the boat was going the same speed and if the boat was going faster than the waves, and try and draw what you think that would look like. Okay, go ahead and pause and do that now. Okay, welcome back. You can check the answers to this by clicking on this link. And I actually already have this open. And here it is. And so here's the same question. We can see the answers here. A boat going slower, a boat going the same speed is going to have all of, I can't move the cursor, but it's going to have all of the waves, this little ring here in B, the ring with the dashed lines, all the waves are going to be bunched in one spot. And then for picture C, the boat is actually going to be ahead of the waves. So the waves are all going to slow down behind it. And then actually they'll bunch up in the front, kind of like you see there in B. And so that's important because that takes us to this concept of a sonic boom. So we're going to watch this video on the sonic boom together. And so let's take a look at that. Okay, so this is the video. Go ahead and click on the link. I've given it to you here. It's 3 minutes. You should watch it on your own in the highest resolution that you can so that you can see the videos. We've got some questions here, and then when you're done, come back and we will go over the answers. Okay, so to help go over the video, Jackson's going to talk about what some of these things do. Lily, you want to say hi?
Hi.
There she is. Okay, Jackson, which planes do you have?
I have this plane.
What kind of plane is this? What kind of plane is that?
A jet.
A jet. That's right. This is a Blue Angels jet. This is a Hornet, but it's not a murder Hornet.
This is a
Okay.
jet.
It is a jet. What kind of jet is this, Jackson? Can you hold it up so they can see? What kind of jet is that? You don't remember?
No.
SR-71 Blackbird. Grandpa worked on that.
Can I have?
What's this?
No.
You don't need that. What's this?
A rocket ship.
A rocket. That's right. Here's a rocket. We're going to look at one of these later. All right. Cool.
What about the other ones?
What about those other ones? What's this one?
A police airplane.
Police airplane. Okay.
That has the front part on the back.
Okay. What else do you have? Gotta make it quick.
I have a transformer. And I have another jet.
A-10 Thunderbolt 2. All right. Good job, buddy. Thanks. Okay, so we'll see some of these, or you saw some of these in the video. We saw the SR-71 in the video, this one right here, and it moves incredibly fast, fastest plane in the world. And when it's going that fast, thousands of miles per hour, it changes the pressure in the air, and that causes a difference in density, and that bends light just like a lens. So in the same way that you might look at a magnifying glass or maybe a cup of water and see it bend light, this thing moves so fast through air that it bends light. And so we see that right here. All right, these are the waves showing us that. And what else? Okay, so I gave you some examples of lenses, magnifying glasses, cups of water, other bodies of water. What about the difference in density bending light in the picture of the Blue Angels number 5 Hornet? So we can see that here. This is actually in my hometown. This is in Oakland, where the Blue Angels fly every year for Fleet Week. And if you look closely, and you may not be able to see it here on this video, but if you watched it on your own, you can see there's a triangle right here. It starts at the right behind the wing, just in front of the tail surfaces here, and goes up to about there. And then it's vertical here, and you can see it's impacting the water down there below, causing a disturbance in the water. And it's also starting to cause a cloud to form because the pressure changes are causing enough changes in the air to make it that it can't hold water anymore. And so the clouds are showing up. Okay, so that's a shock wave right there. And we see the clip of the rocket at the end. This is pretty amazing. So I've got this rocket here. I'll let it play.
Of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result.
Oh, there they are. So the weather was just right, the moisture was just right, the temperature just right, that when the rocket went through, the waves that it created, the pressure changes that it created, uh, caused a visual ripple, something that you could actually see. That happens all the time, but you usually can't see it because there isn't enough moisture in the air. But that time you could. It's pretty amazing. Okay, so there's more info on sonic booms if you want to read about it. And then everything else for today is the beginning of looking at electromagnetic waves, so waves that we can't see. We started with waves that you can see, that you can feel, mechanical waves, things that you can, whip a hose, a string, and see the wave propagate or move. And talked about interference, where we could see it, right, with sound and things like that, or we can feel it. And now we're going to move on to stuff that we can't see. We can see the effects of it, but we can't actually see it with our eyes. So that's electromagnetic waves. And the best way we're able to perceive this and perceive the effect of it is through light. Right? We can't actually see light, but we can see the results of it, the reflections that come from it. And so, yeah, that's what we're going to be learning about. So there's a handout on Schoology, and the reading is from a conceptual physics book, and that reading is available here. And tomorrow we'll have a little quiz on mechanical and sound waves, and you'll also have time to finish the guided reading. And that is it. So have a great rest of your day. See you later.